Yeah, so thanks everyone for coming. Really pleased today to have Roman Vershynin here from UC Irvine. And with that, take it away. Thanks.
Yeah, thanks, Joe. Thanks everyone for coming. Feel free to interrupt me at any time. This talk is based on our joint work with March Boidi-Harju and Thomas Stromer, and myself. The starting point of a lot of progress in combinatorics in the past maybe half century is the Szemeredi regularity lemma. It says basically that any graph, and this is my visualization of a vertex set of the graph, any graph can be decomposed into almost pseudo-random graphs, plus a small outlier. And more precisely, that means that any graph on vertex set V with edges E, and for any accuracy that's desired, epsilon, one can decompose the vertex set into little parts, VIs. Let's say this is V1 and this is V2 and this is V3 and so on, in such a way that except for the small part, which I'll ignore for this purpose, most of the other parts are good. And that means that the induced graphs on any pair, VI, VJ, are almost pseudo-random. For induced graphs, you just look at the V1 and V2, and just look the edges that are crossed from V1 to V2. Okay, bipartite graph. So they are almost epsilon pseudo-random. Technically, this means that if we look at any subset here and any subset here of vertices, and we ask how many edges cross from X to Y, that number will be proportional to the sizes of X and Y. So pseudo-random, let me let's say it more precisely. So for any X in the V1, for any Y in V2, VI, VJ, let's say, so that they're not extremely small. Otherwise, of course, there will be effects of too sparse graphs. So not too small. If you look at the number of edges, they will be proportional to the sizes of X and Y. VI, VJ. That number is less than epsilon. So, okay. So this is kind of full disclosure on Szemeredi regularity lemma. And most means that I'm excluding an epsilon proportion of the graph. This is a remarkable result that led to a lot of progress in combinatorics. Like I said, the nemesis of this result is the size, the number of parts required. This grows really fast. So C of epsilon is large. I can't remember what it is, but it's like a tower in 1 over epsilon. And for some time, people believe that that's not right, that it should be improved to something like exponential in epsilon, but that was not true. It should be like that. The example of Gowers dashed all the hope in that direction. 97. And Szemeredi is from 75, 78, something like that. There are versions of Szemeredi regularity lemma for smaller number of parts. These are weak regularity lemmas. In fact, there are one can deduce one from the other. But Fries and Cannon were the first in 1999 to obtain weak Szemeredi regularity lemmas whose conclusion is a little bit weaker, but on the other hand, with C of epsilon that's nicer. C of epsilon will be just exponential and 1 over epsilon squared, I think, or something like that. We'll state that, the result. And it would be useful to depart from combinatorics and just state it as a result about matrices, adjacency matrices in this particular case, adjacency matrices of the graph. But in general, their result is about any matrices. And that's how the weakening of Szemeredi regularity can open the range of applications for it, because now you look at any matrix, let's say n by n, whether it is the adjacency matrix of the graph or not, doesn't really matter. And what you would like to, so for the adjacency matrix, the rows and columns are the vertices, and you're decomposing the vertices like this. And so this picture that I showed you is illustrated here. Here we're decomposing this into V1, V2, and V something. And this is V1, V2, V something. And the conclusion of the strong regularity lemma is that if you look at, let's say V1, V2, this part is almost, looks like a random matrix, or a pseudo-random. So in the matrix form, Szemeredi regularity says something like any matrix can be decomposed into a small outlier and a bunch of pseudo-random matrices. And let's state that weak form in the Fries and Cannon version of it. For that version, we would like to approximate any matrix, any n by n matrix, by a sum. Sorry, by the matrix that's flat on each block, which means that all the entries in each block are the same. The error in such decomposition will be measured with respect to the so-called cut norm. This is the right norm for combinatorics, for counting the edges, and it is defined as, think about the spectral norm, the operator norm. How do you compute this, the operator norm of a matrix? Just L2 to L2. You would take the quadratic form in the entries like this in A, and then you take the supremum of it, maximum. In the operator norm, you'll take the maximum over all unit vectors, Euclidean unit vectors, x and y. And for the cut norm, you change that. You take supremum with respect to 0, 1 vectors. A little, just maybe like 3 minutes thought or something, and you would see that that you can replace 0, 1 by minus 1, 1. And with minus 1, 1, this will be equivalent. Replace up to some constant factor, you will pay something. So and then for minus 1, 1s, this is the same as the operator norm, but not from L2 from L infinity into L1.
Matrix is not positive elements, no?
Not necessarily, no. In this, in this case, no, it should be okay. Yeah. So Fries and Cannon theorem. Fries and Cannon. 99 theorem. The weak Szemeredi regularity says that for any matrix A, and for any desired number of parts in the decomposition, there is a partition with that many parts. Here we're just decomposing this set of indices. They denote our vertices into 2 to the r parts, such that, and the error is in the cut norm. Let me normalize it by 1 over n. Is less than 1 over root r, and here's the Frobenius norm of A. Okay, that's what they get. What's a decomposition? So what's B? B is just a matrix obtained by averaging the entries of A on each block, on each block ij.
What is Frobenius norm?
Well, Frobenius is Hilbert-Schmidt norm. It's
Okay.
yeah, this is just you sum everything aij squared like this, and then you take the square root. That result is also very important, and there's a million of different versions of it, and we'll see one more version in this talk. Before you go on, any other questions? Everything is good? Okay, so once we did, like I said, cut norm, this thing, the cut norm, is kind of the right norm in combinatorics. And if you look at the graphs, because you are kind of cutting off a little bit submatrices, but it is not such a natural norm if you forget combinatorics. So if you don't know what it is, maybe it's not the most natural matrix norm that comes up in analysis or linear algebra, computer science. And so a natural question would be, does Friese-Gannon theorem still hold, or something like that still holds for more natural norm, for spectral norm, for Frobenius norm, Hilbert-Schmidt? We already have this Frobenius norm on the right-hand side. Can't we have Frobenius norm on the left-hand side, for example? Can we do that? In fact, the cut norm, let's look at this one. If you just literally apply Cauchy-Schwarz to it, by Cauchy-Schwarz, this is less than aij squared times 1/2. Not Cauchy-Schwarz, probably it's yeah, it's Cauchy-Schwarz, yes. So that time xi's and yj's are either 0 or 1, so they're at most 1, so they disappear. So this is the Frobenius norm. So the cut norm is bounded by the Frobenius norm. It's weaker, and we have something for the cut norm. So the question is, can we have this? Can we have a result for the stronger norm, for the stronger norm of the error, the Frobenius norm, and more natural one?
One second, Roman. I think it's multiplied by n or square root of n or something like that. Cut norm is not bounded by Hilbert-Schmidt norm.
Oh yeah, yeah, you're right. I forgot the xij. Oh yeah, yeah.
Times
Yeah,
n.
you're right. It should be okay. Let's do it properly. This should be root n, maybe. Root n is good. N.
N, yes.
N is good. Yeah, I forgot. Yeah, thanks, Sasha. This factor of n actually appears here, so I forgot to divide by n.
It corresponds r equals 1. Yes.
Yeah. So the cut norm is bounded by n times the Frobenius norm, and so if you divide, and once you divide in the left-hand side by n, you get the Frobenius norm. So the question is, does it hold for the Frobenius norm like that? Okay. It is not true that it holds for Frobenius norm or operator norm without any assumptions. There are some results about that. Deshpande, Gannon, and Srivastava in 2012 proved a result for Frobenius norm or Hilbert-Schmidt norm. For low rank matrices. If the rank, the upper bound of the rank is something like log n, then it's something is possible to do. What we will do today is we will get rid of any rank assumptions, but we'll assume instead that the matrix is positive semi-definite. So we'll prove a weaker Szemeredi regularity for any positive semi-definite matrix. Here we go. So here's our result. Theorem. For any positive semi-definite n by n matrix A, and for any desired number of parts, this is just like before, there is a partition into 2 to the r parts, such that, and here we have the Frobenius norm, I will divide this by n, and it is less than 2 root r times the max entry. So this one is just the L infinity norm. This is maximum entry in the absolute value. B, just like before, it averages A on this partition. And yeah, that's the result. Maybe just to understand what this really means and why this normalization is natural, let's square both sides. And in the left-hand side, we have this squared. Yeah. The right-hand side will have this maximum Pij. So the error that we're looking at, this error, is just the L2 average error per entry. It's the average error per entry in the L2 sense. And we claim that we can make it decay because of the R, and the normalization is just a max entry here. Another little remark before we go to the proof is that nothing really depends on n here. As long as you understand this as normal, as an average of all entries, then nothing really depends on n, and you can just let n go to infinity and automatically establish the same result for kernels or matrices. For functions on the square 0, 1. Any positive semi-definite kernel, because of this theorem, can be approximated by kind of step functions, by functions that are flat on each block. I'll not write this down explicitly, but it's a little exercise just to translate this into the continuous setting. Good. So here's the plan. I'll give a complete proof of this. We have like 30 minutes. I'll give a complete proof of this result. The proof is probabilistic, and I think it's instructive. It uses a little tricks that many people would enjoy and hopefully apply. But before doing this, any questions about the result? Good.
Can you see from this equation why maybe this 2 to the 1 over epsilon squared is necessary versus the tower of 1 over epsilons you mentioned earlier?
The tower applies for the strong Szemeredi regularity, so this doesn't explain any of that. This is a weak Szemeredi regularity result, and here
you see
2 to the r. Mm-hmm. So if you let this be like 1 over epsilon, this will become, like if 1 over root r is epsilon, then I believe 2 to the r is what? 2 to the 1 over epsilon squared, maybe?
Great. Yeah, that helps.
Yeah.
Thank you.
Mm-hmm. Yeah. So that's a number of parts. It's the same as in Friese and Cannon result. And we can, in fact, show that it is optimal. We can improve it beyond 2 to the epsilon 1, 2 to the 1 over epsilon squared. Good question. Yeah, anything else? Good. Okay, guys, why don't we prove this? Let me clean this up. Delete, it will be fun. So let's restate this result in the probability language. I'll restate it now, and it may not be immediately clear why this is the same, but I'll explain why. So for any random variable x, I'm literally writing something equivalent to the theorem. For any random variable x that is bounded by 1, almost surely, and the rest is the same for any r, there is a partition. There's no n here. There is a partition of the sample space into 2 to the r parts, such that the associated sigma algebra generated by this partition satisfies the following. So you look at the inner product between x and x prime, where x prime is an independent copy of x. You compare this with y prime, where y is the conditional expectation of x, and y prime is its independent copy. And this is the error, y squared 4r. Okay. So let me explain how this probabilistic theorem implies the usual theorem. In the usual theorem, first of all, without loss of generality, we can assume that this is 1, just by rescaling. So without loss of generality, we assume that the max entry is bounded by 1. A is a positive semi-definite matrix. And as such, any positive semi-definite matrix is a Gram matrix of some vectors. This simply means that the entries are the inner products of xi, xj. You can always realize any positive semi-definite matrix as inner product of some vectors. It follows simply from spectral decomposition. Okay, so this assumption means that every entry is bounded by 1. In particular, the inner product with itself is bounded by 1, xi. That's a norm of xi squared, bounded by 1. So this means that norm of xi's is bounded by 1 for any I. So A, our input matrix A, is a Gram matrix of some system of vectors that are small, that are bounded by 1. For simplicity, let's assume that this actually is, they're all equal to 1. And then we make this transition into probability. So we apply this probabilistic theorem for the random vector who is uniformly distributed on this system of vectors. And that's all. So if x has uniform distribution on this system of vectors, then what is x prime, if x prime is an independent copy? Well, it's xi inner product with xj, where I and j are taken independently. But xi, xj is exactly are the entries of A. What's the conditional expectation? Conditional expectation makes a random variable constant on the parts of the partition. And that literally means that we're averaging on that part. So that gives us a matrix B here. This is Aij This becomes aij, and this becomes bij, and then we square them, take the expected value. What's expected value with this? That's just the sum of all the squares normalized by n, and that's it, by n squared, and that's it. So we see that this theorem implies this. The other direction is easy, but we don't need that direction. Varsho good? Okay, so now we can forget. We first forget combinatorics and move to linear algebra, and now we're forgetting linear algebra and moving to probability. So now we have this probabilistic statement, which we are about to prove. We clean up here. All right. The proof of this result is based on, will be based on acute inequality due to Grothendieck. Alexander Grothendieck. Actually, not inequality, identity. He does have inequality, but the identity that I am referring to appears as a main part of the proof of his inequality, in fact. So Grothendieck's identity, 1953. This one is simple. Fix any two vectors that are unit vectors on the sphere of dimension n in n-dimensional space. So fix two vectors like this on the sphere. This is x and this is x prime. And look at the Gaussian vector, the standard normal vector in the space. And let's compute the sign of the inner product xg times the sign of the inner product x prime g prime, x prime g, sorry. So in this cone right here, in this cone, just bordered by x and x prime, the sign takes value. This is plus, and this is plus one. This is plus one. So the value of the product of the signs is positive. By symmetry, the same happens here. Also positive. So here it's positive. Here it's positive. And on the rest of the space, one will be positive and the other will be negative. And plus one times minus one is always minus one. So this random variable, this one, takes positive values here, negative values here. And it's rotation invariant. And what I'm getting is you can just now compute it directly, just using the trigonometry. It will just depend on the angle between x and x prime, obviously. Not the orientation, just the angle. And if you do this trigonometry, it will be the arc sine of the angle. Sorry, it will be the arc sine of that will be the angle. So here is a precise version of this result. That's when you work it out. The sine of this equals x and equals the inner product. Okay, that's a little exercise to check. Okay, so far so good. Okay, so we will now use the empirical version of the Grothendieck's identity. And by that, it's just a fancy way to say that instead of sampling from one Gaussian and just population expectation over all like Gaussian, I'll take a finite sample of Gaussians, R of them specifically. And instead of taking the population expectation, I'll take the empirical expectation on the sample. So here's what I exactly mean. Let's call this fx, x prime, fg, let's say. So I'm doing the same thing, pi over 2, but except instead of taking the expected value like this with respect to g, I'm taking the average over a sample. Sine x g, maybe gi, sine x prime gi, where gi's are independent and identically distributed normals like this. Now, by the law of large numbers, the empirical mean converges to the true mean, and the sine is a continuous function. So by law of large numbers, we have almost surely, when r goes to infinity, the number of them, this will converge to x prime. Yeah. Let's compute the error of this approximation for finding r.
Thank you.
Okay, let's compute the error. This will be the difference x prime minus fg x prime. That's going to be simple. Well, let's compare. So we're looking at this versus this. Yeah. So when we subtract one from the other, the sign, the nonlinearity stands in our way. However, the sign is a Lipschitz function. It's actually one Lipschitz function. And because it's one Lipschitz, we can pull it. So the sign is one Lipschitz. And that means I can just pull it off like this. So it's pi over 2 times. And then I can bring 1 over r expected value like this inside. So let me call, maybe I call this one's xi's. Then this will be, and these things are expected value of xi's. Sorry, this thing, expected value of xi's. Okay, so just have the difference now between the true and expected value, the true value and the expected value. So xi minus expectation of xi. Yeah, agreed. Everything is good. So I only use this get rid of the sign by Lipschitz, and that's it. So far, so good. And then this happens for any realization of G. So what I do, I take the expected, I square the thing, x prime minus fg. And remember, I want to take the error, so this will be the L2 error here. So square, take expectation, and what do we see? Voila, we have here we have here we have expected value of the square of this. That becomes just the variance of the sum. So pi square over 4, and then there is r squared, and then there is variance of the sum. And the variance of the sum, they're independent random variables, equals the sum of the variances. Well, each ci is plus or minus 1. That's how we define it. It's just a product of signs. And so the variance then is less than 1. And yeah, and we got it. So this is p squared over 4r. Yeah. Okay, so just as expected in the law of large numbers, the error should go down as 1 over root r, or the sum of r independent random variables, and it does. Here's r, but it's squared. So yeah, so it's a classical error decay in the law of large numbers. Perfect. Nothing new happened here. What we do now with this is this happens for any fixed pair of vectors. Now we substitute a random pair. Remember, our ultimate goal is to prove something like this. And so now we're substituting the random x and its copy, x prime, into this equation. X and x prime is x prime, and we take expectation with respect to x and x prime on both sides. And we have this random thing now. So x prime like this. Squared is less than pi square root of 4g or r. Good. Okay, so now what we do is we apply Fubini. Let me do it here like this. The expected value of g, expected value of x prime. This inequality means that there exists a realization of g for which this bound holds. So there exists a realization of g such that this holds. Actually, it's not just g, it's g1, g2, g3, and so on and so forth. Remember, this is our sample. So there exists a realization of g1, g2, etc. through gr, so that this holds. Perfect. And we are one step from the conclusion. Let's just keep track of what we actually wanted to prove. We would like basically to approximate the inner product like this, or any random variable, by a simpler inner product where y is averaged copy of x. And this inequality goes into that direction. We approximate the inner product between x and x prime by something. Well, what's that something? Fg. What's Fg? Fg is this. Fg is kind of simple because it depends only on the signs of R vectors. So if we take the sigma algebra generated by those signs, like this, generated by those signs, then that makes Fg, this one, measurable with respect to the product sigma algebra. You agree? It depends on those signs. It's literally expressed in terms of those signs. So if I take the sigma algebra generated by these signs, then this Fg is measurable. So this makes Fg x and x prime f cross f measurable. So let's call this z. That's a random variable. Z. What do we know about? Well, what do we know about sigma algebra? First of all, the signs. How many signs do we have? We have 2 to the r signs, right? So the sigma algebra is generated by a partition of a sample space into 2 to the r parts. It's just because how many values does this thing has? This can have 2 to the r values, and so the sigma algebra must then be generated by 2 to the r parts. So we have the sigma algebra as required. We have and the conclusion is now that we approximated x prime by some random variable that's measurable in the sigma algebra as we require. And the final step is simply to say that once we have it for some z, that z must be the conditional expectation, because the conditional expectation is a projection in L2, is the best approximant. So the conditional expectation is a projection, is an orthogonal projection in L2, which basically means that it's the best possible approximation. So if we have approximation with something here, measurable, we must have even better approximation with the conditional expectations over y would be the conditional expectation of x into f. Done. So that's the entire proof. It's based on kind of randomized rounding scheme that goes back to Grothendieck, and that's it. That's our proof.
Can
Go ahead, Sasha.
one use the same type of tricks to prove original Cannon-Fraser?
I haven't thought. That's a good question. I don't know. There is the problem with Friesen-Cannon is that it expressed. Here we go. That there is a maximum. It's this maximum of quadratic forms, and the maximum is highly non-convex and non-nothing, and so I don't really know how to pull the maximum through this. What we prove is for the Frobenius norm, and that's basically L2. And I know how to prove how to pull L2 through everything. And that's what we did. But for the maximum,
isn't what you prove maybe even equivalent to Grothendieck? No.
Grothendieck inequality, you mean?
Yeah.
Or Grothendieck?
Yeah, Grothendieck inequality. I mean,
might
it's
be
so close that maybe you can reverse the argument. No.
It may be. I don't know. There is the Grothendieck. The proof of Grothendieck inequality basically goes like this: you first prove this identity, that thing. Now, if there was no sign here, no nonlinearity, then you can that's basically Grothendieck inequality, because these things. So basically, this identity allows us to replace the products, the sums of products of numbers by the inner product of vectors. That's what Grothendieck inequality says. The only problem there is a sign, this nonlinearity. And what Grothendieck does is he kind of linearizes sum by embedding the inner product into higher dimension. And there he uses what we call the kernel trick. The sign was also a problem for us here, but we just use that sign as one Lipschitz, so we get away with it. It was much simpler thing. Whether that can be done on the level of Grothendieck, I do not know. Probably not. Yeah, that's a good point. Yeah.
And one more question. So this was about matrices. What if anything about tensors?
Oh yeah.
Well, tensors cannot be probably positive semi-definite. I don't know.
Yeah. Right. So positive semi-definite we needed very crucially because we wanted this to be a Gram matrix.
Yeah.
So I wanted somehow to relate this. And then what? Okay, so then general form. I don't know. That's a good point. Yeah, I don't know.
Joe knows why I ask.
What's that?
Joe knows why I ask.
Yeah, Sasha took my question.
Yeah. Okay. So you work on tensors, guys. Yeah. Okay. Okay, guys. Can I do one more application? Maybe 5 minutes. Possible?
Oh, please.
Yeah.
Okay. 5 or 10 minutes, whatever you need.
5 minutes. Okay. Perfect. So we discovered this result. This new type of weak Szemeredi regularity by accident. Actually, it was a byproduct of what we actually wanted to prove. And what we actually wanted to prove is the theorem about is there is a bound on covariance loss. It's a cute question in probability. You guys know the law of total expectation, right? So if x is a random variable and y is conditional expectation with respect to any sigma algebra, then the law of total expectation simply says that expected value of y is expected value of x. So there's no loss there. Okay. You can ask, what about variance? The law of total variance. There is some loss, right? If you take the full the expectation of the entire sigma algebra, The variance is killed completely. You get a constant out of it. So there is some loss. What is this loss? So this is going to be positive always. And if you work it out, this is a simple identity, expected value of x minus y squared. So as you can see, it's positive, and so we say that there is some loss of variance. All right. For random vectors, you can do the same thing, but instead of the variance, well, the law of total expectation holds, of course, but the law of total variance, there is some analog of it. What's a higher dimension version of variance? It's a covariance. Covariance metrics. That's a proxy for the notion of variance, and this is denoted. This kind of expected value of x minus mean squared, but in the metrics terms, the square is this. And for the covariance, the analog of this becomes sigma x minus sigma y, x squared, kind of, y squared, kind of. And this is x minus y squared, kind of. And this is obviously a positive semi-definite matrix. So again, there is a loss here in the positive semi-definite sense. Okay, so this is just linear. It's very simple to check. Main question is, how much is that loss, and how can we minimize it for a given budget? So if let's say, if our sigma algebra, of course, if the smaller the sigma algebra, the more coarse sigma algebra, the more you will lose, definitely. But how much more? Let's say, suppose the sigma algebra is generated by k parts, partition into k parts. What is the best sigma algebra? What is the best covariance loss? So find, for a given distribution, find the best decomposition so that the associated covariance loss is the smallest possible. How much is it? And this is the theorem bounding this. We first proved it with March, Bodiharjo, Stromer, and myself, and then Jane, Sa, and Sony removed the logarithmic, the iterated log factor that we had there, log factor. So here is the result on the covariance loss. X be any random vector, normalize it so it lies in the unit ball like this. Then for any budget, for any number of parts, we can find the partition of the sample space into this many parts, into 2 to the r parts, such that the sigma algebra generated by this partition is good. By this partition has a small covariance loss. So sigma x minus sigma y, and the smallest possible in the Frobenius norm. Remember, these are matrices. So in the Frobenius norm, the smallest is, I think it's going to be pi over 2 root r. And this is optimal. I'm not sure about constant pi and 2, but the rate of decay is optimal. So this is basically says how, you give me the random vector, you give me the distribution, and I will find the parts. So that if I flatten the distribution on these parts, make it a kind of density, a step function on these parts, then the covariance loss will be as small as it can be. And that's what it is. So how do we, well, this is a direct consequence of the weak Szemeredi regularity. Let me show you how this is done. Let's square this thing. So it's that. I'll just rewrite this. Expected value XX transpose minus YY transpose squared. Frobenius norm. Squared. Now a little exercise. This is like, I don't know, 10-minute exercise maybe. to show that the conditional expectation is actually roughly points in the same direction, not opposite. So this is smaller, I think, than XX transpose minus YY transpose for Frobenius norm, like this. So the conditional expectation forms a non-trivial positive angle with the actual one. Okay, and then another exercise is to show that this is equal to the quadratic error, where X prime and Y prime are independent copies of X and Y respectively. Done. So this, we reduced the problem about covariance loss to the problem about to the probabilistic version of weak Szemeredi regularity. And by the theorem that we showed on weak Szemeredi regularity, we bounded it by pi squared divided by 4r. That was our bound. And that's it. So we proved the covariance loss just as a consequence of that. The original proof was much longer. And Jane Sony is also much longer. This is now a very clean version of it. Okay, I should stop here.
Thanks so much, Roman. We have time for any questions people have.
What was the iterated logarithm?
It was, so I think we originally had it over here, maybe. I can remember like log r, maybe over here.
So the argument is slightly different?
Yeah, the argument is totally different. Yeah, we didn't realize any connection, that there is any connection with weak Szemeredi regularity back then. And so we just beat our heads directly against this question.
Okay, thank you.
There was some loss there. Yeah. And then these guys, they did another direct proof, but removed the log factor. And now it's just part of the general framework, I guess.
So I suppose a tensor version of this could be interpreted probabilistically as well. So you're interested in, the higher moments where you have.
Oh yeah. This This one should have a tensor version, right? Because what's covariance? There's covariance tensor. It's like this one will be expected value of x tensor x tensor x tensor x, whatever. And yeah, that'll be interesting. Minus this and then this. Yeah, so it's a simple, you take simple tensor and you take expectation of it. Okay. There's probably no way of saying that this is positive semi-definite or something like this, right? There's nothing like that for tensors. Yeah.
Yeah, I'm not familiar. I'm sure somebody has tried to define this.
Yeah, because you can take it as, you can always take this supremum over, or not supremum, you can take the multilinear forms and require them to be positive. Yeah, I don't know. And they are positive probably for even exponents, but what do you get from it? I don't know. Yeah, it will be a nice question. Frobenius norm is just, just the square of all the sum of the square of all entries. So it's just for tensors will be the same thing. So yeah, here we have a nice question. We did part of that question in our paper, in our original paper. This, like with the root log or something. So we did this, and there was some terrible, I remember there was some terrible dependence on the rank, not the rank, but what do you say, the degree of the tensor. Yeah, it sounds like 2 to the d maybe. And because R itself is a log of the number of parts. We're beating it against 2 to the d. So log number of parts versus 2 to the d, that becomes doubly exponential. So yeah.
I see. Thank you.
Hmm.
Roman,
Yes, Tasha, did you want to say something?
yeah,
You're cutting off.
so how to imagine what you're doing? You have a matrix, you split the rows and columns to some special subsets, such that if you look at every block, you have the estimate of the Hilbert-Schmidt norm of the block and the average, right?
Yeah, and we actually, yes.
And the average, and you divide by n squared.
Yes. So it's an average error per entry, which is
Average error per entry. Why it's natural to approximate?
because it naturally takes if you take the limit as n goes to infinity,
Mhm.
it becomes just a L2 error of the functions on the square.
Uh-huh.
for
And
instance.
like you still split to finitely many pieces, right?
Mhm. Yeah, same thing. Nothing depends on n, so it's the same result. Yeah.
And one cannot do it for function like directly. What kind of function it will be a priori? It will be just bounded.
No, it would bounded
bounded.
and also positive semi-definite. That was important.
Yeah. So positive.
It needs to be positive semi-definite kernel. Yeah.
Right. Some combinatorial property. Yeah.
Yeah. What is this theorem called? Like, Mercer theorem.
Okay. Thank you.
Mhm.
No, not quite. How
Not
about
quite.
s? How about n squared goes to infinity? It's just L2 norm will be right. Just
L2 norm. Yeah. Exactly.
Okay. Thank you.
Yeah. Mhm.
All right, we're at the hour. Anyone has a very last minute question, feel free to ask it. Otherwise, I'll thank the speaker again. Thanks so much, Roman, for a wonderful talk, and see you all next week.
Thank you for inviting, John. Thank you everyone for coming. It was really
Thank you.
nice.